Welcome to a lesson with Dr. Pal. Let's talk about alternating series. What is an alternating series? Well, it's something where the terms bounce around between -1 and 1. So often when we just multiply by a power of -1 and where the exponent is increasing by 1, that often accomplishes that purpose. All right. Also, then let's suppose we're multiplying it to some terms. That's an n, and over something like n squared. Maybe this is n plus 1, maybe this is n squared plus 5 or something like that. Okay, so this is alternating. Now we can achieve the alternating pattern by doing something like else, even like cosine, like switching sign back and forth between positive and negative. Maybe we could do even something like cosine of pi n on the unit circle. When n is 0, we're at an angle of 0. So that's like a 1. When n is 1, we're at like pi, which is like -1, x coordinate of -1. When n is 2, it's like 2 pi, we're here. 3, we're there, bouncing between -1 and 1. There's different ways to bounce around between -1 and 1 and changing the sign from term to term. Now, when do alternating series converge? Let's suppose that we start at a particular value. Where in our sum we've added up to this point so far. Then the next term that we add, maybe it's a negative term, so we actually subtract so far. Let's also suppose that we have the condition that the absolute value of the terms is decreasing, meaning that if I've subtracted this much, next time when I add, I won't add as much as I subtracted. And then when I subtract again, I won't subtract as much as I added before in absolute value. And I go like this. Now, if I have that condition so that the absolute values are decreasing, then I'll have something like this. It looks like it's kind of narrowing in, right? And maybe hopefully it narrows in to actually converge to something. Well, one thing's for sure, the top lines themselves, if you just look at the sequence of top lines, they're going down. It's a decreasing sequence. And it's even bounded below. You'll never get back to here again. So it's decreasing, bounded below. Monotone convergence says that the top lines actually converge to something. Likewise, the bottom lines are increasing and bounded above by this first top line, which means that that they actually converge themselves by the monotone convergence. They're up to something. What we want these two guys to converge to the exact same thing. How do we get them to converge to the same thing? Well, as we're adding along, we just need to ensure that what we're adding by itself actually goes to 0. And then it'll actually make those two things hit, or not hit, but converge and go together. So we need that the limit of the terms themselves, so the terms themselves actually have to limit to 0. So we have some conditions. If a sequence is alternating, the absolute values are decreasing, and the terms themselves go to 0, then the series, the act of adding up everything, will actually have a limit. All we have to do to show convergence is just these three things. Alternating, absolute values going down, terms go to 0. And then we know that our alternating series will actually converge. Let's look at this particular example now. We know it's alternating, so the first thing is satisfied. Is the absolute value of the terms decreasing? Well, this is like a function, and if we put an x in here, what we need is that eventually this is like decreasing, which means eventually the derivative of this is negative. So let's take the derivative of this. Quotient rule, x squared plus 5 squared on the denominator. Derivative of the top is 1, so we have times the bottom, x squared plus 5, minus the top, which is x plus 1, times the derivative of the bottom, which is 2x. All right. Now let's just consider the leading term. X squared, and this you get a minus 2x squared from here, which means the leading term is going to be negative x squared. Negative x squared, a positive bottom. Oh, yeah. So eventually, x is large enough, the leading term wins, and it looks like the derivative is negative, meaning the absolute values are decreasing. It's alternating. Absolute values decreasing. Do the terms go to 0? Let's see. All right. Well, if we take a limit of this as n goes to infinity, bottom has a higher degree than the top, it should go to 0. In fact, with L'Hopital's rule, you could see that derivative of the top is 1, derivative of the bottom is 2n, and take that limit, which should be the same as that limit, and apparently, as n goes to infinity, yes, this goes to 0. So the terms go to 0 as well. So all three things are satisfied, which means that this series, even without knowing what the sum is per se, we just know that it converges. Now, in what way does it converge? It converges as a sequence of partial sums. In no other way does it converge. You can't rearrange it to convergence or anything. It doesn't converge absolutely with the absolute values necessarily. I mean, sometimes alternating series do, but actually you can actually do a comparison check and compare this to 1 over n if we took the absolute values, and we know that series actually diverges. So this series actually will diverge in general if you were to take the absolute values. However, if you only look at just the sequence of partial sums only, that's called conditional convergence. That's the normal type of convergence that we focus on when we're just looking at a sequence of partial sums. That's the partial sum sequence convergence. Absolute value or absolute convergence is the partial sum sequence convergence of absolute values. So they're both partial sum sequence convergence limits. However, we use the idea conditional when we're saying let's not put absolute values on, let's be sure not to. That's what we mean when we say conditional. Absolute convergence just simply means put absolute values on, and then we always look at the limit of the sequence of partial sums. Thanks for watching.